Good morning to everyone. Here, Nanajayam G, studying Electronics and Communication Engineering at Government College of Engineering, Tirunelveli. In this video, we've seen about what I learned in Emertxe Embedded System Internship. What we learned: basic C program, embedded system, types of embedded system, microcontroller, difference between microcontroller and microprocessor, Fixing Lab and MPLAB XIDE. Basic C program. Data and variables. Simple data types available in C programs are integer, float, character and double etc. And I learned how to declare a variable and initialize a variable. Operators are arithmetic operator, relational operator, logical operator, bitwise operator and assignment operator. Control flows are conditional statement, loops and jump statement. Conditional statements are if else and switch cases. Loops are for loop and while loop. These are iterated depending upon the condition. Jump statements are break and continue. The difference between break and continue are break terminates the loop, but continue terminates the iteration. Basic data structures available in C programs are single dimension array and string and pointers. Pointers are used to specify the address of the variable. Function in C program. A function is like a named mini program inside your main program. It performs a specific task and you can call it whenever you need the task done without rewriting the same code every time. What makes a function useful? Modularity breaks your program into smaller, manageable parts. Reusability write once and use many times. Clarity makes your code easier to read and debug. Abstraction you can use a function without needing to know how it works internally. Function declaration return type, then function name, then parentheses. Inside the parentheses, parameter are listed, finally ended with semicolon. This is syntax for declaration a function. What is embedded system? An embedded system is like a tiny computer built into a machine or device to do a specific job. It's not like your laptop or phone, which can do many things. This kind of computer is designed to do one job really well, like controlling the timing in a washing machine or managing speed in a car. Simple example: a micro oven has an embedded system that controls how long it heats your food. A smartwatch has one that tracks your step and heart rate. A remote control car uses an embedded system to move when you press button. Key components of embedded system. Microcontroller or microprocessor is the brain of the system. Memory. ROM for program storage and RAM for temporary storage. ROM is non-volatile memory and RAM is a volatile memory. Input-output interfaces are sensor, switches, display, motor and etc. Software are code written in language like C, embedded C or assembly. Power supply. Often battery power are connected to regulated source. Characteristics. Task specific. Perform one or a few dedicated functions. Real-time operation. Response to input within strict timing constraints. Compact and efficient. Small footprint, low power and cost effective. Reliable and stable. Designed to run continuously with minimal failure. How it works: takes input from sensor or user interaction, process data using with microcontroller, generate output to control device or display information. Examples in daily life: smartwatch checks your health and tells you important things. Microwave oven manage cooking times and power levels. There are four types of embedded system. First embedded system is standalone embedded system. This system works independently without needing to connect to a computer or network. They take input, process it, and give output. All the hardware and software needed is built into the device. Examples: microwave ovens, calculator, washing machine, digital cameras. There are two types available in standalone embedded system: slave embedded system and independent embedded system. Slave embedded system. This system depends on another system called the master to give them instruction. They don't work on their own. They only respond when the master sends a request. Example: a temperature sensor that sends data to a microcontroller only when asked. Independent embedded system. These systems work by themselves without depending on any other controller. They take input, process it, and give output all on their own. Example: a microwave oven that starts cooking when you press the button without needing help from any other system. The second type in embedded system is real-time embedded system. A real-time embedded system is a small computer built into a device that reacts quickly and correctly to what happened around it. It's designed to do its job within a fixed time, no delay allowed. Real-time systems are classified into three types: hard real-time systems, soft real-time system, firm real-time system. Hard real-time system. These must respond exactly on time. If they are even a little late, it can be dangerous or sketch failure. Examples: airbag systems in cars, medical devices like pacemakers, missile control systems. Soft real-time system. These try to respond on time, but small delay are okay. The system still works, but performance might drop. Examples: video streaming, online games, voice assistants. Prim real-time system. These systems can tolerate a missed deadline once in a while, but the result of that missed task is useless and ignored. Examples: automated factory machines, banking transaction systems. Third type is networked embedded system. A networked embedded system is a group of small computing devices that are connected together either by wire or wireless to do work as a team. Each device does a specific job and they all share data with each other to complete a large task. Example: smart thermostat, ATMs, home security system, IoT device. How it works: each node has its own processor, memory, and input-output parts. These nodes talk to each other using communication protocol like CAN, I2C, Ethernet, or wireless method like Wi-Fi and 6B. The fourth embedded system is mobile embedded system. A mobile embedded system is a small protocol computing system built into a mobile device. It is designed to perform specific tasks efficiently while using minimal power and space. These systems are commonly found in devices that people carry around or use on the go. Examples: smartphones, fitness trackers, digital watches, handheld gaming consoles. How it works: a mobile embedded system works by taking input from a sensor or button, processing it with a small chip, and giving output like showing data or sending it to another device, all while using very little power. Microcontroller. A microcontroller is a small computer built into a single chip. It contains a processor, memory, and input-output parts all in one compact unit. It designed to perform specific tasks, especially in embedded systems like washing machines, microwave ovens, or digital clocks. It works by reading input from sensor or button, processing that input using a program stored in its memory, and then giving output like standing on a motor, lighting up a display, or sending data to another device. Microcontrollers are used in many everyday devices because they are small, low cost, and use very little power. Difference between microcontroller and microprocessor. A microcontroller is a compact chip that includes a processor, memory, and input-output units, all built into one package and is used to perform specific tasks. in devices like washing machine or smartwatches. In contrast, a microprocessor is just a central processing unit and need external memory, input-output ports and other components to work, making it more suitable for general-purpose systems like computers. Microcontrollers are more suitable for simple dedicated functions, while microprocessors handle complex multitasking operations. Peripheral of our project: CLCD display, push button or switches, buzzer, counter model, fan. CLCD display to show current status like washing, rinsing, spinning or error message. Push button for user input such as start, stop, program select or load size. Buzzer used for alerts like door open, cycle complete or error notification. Counter module manage the duration of each washing phase. Fan to indicate that the motor is running or not. Software used in our projects are MPLab XIDE and MPLab XC compiler and fixing lab. MPLab XIDE is used to write our program and MPLab XC compiler is used to compile our program and fixing lab is used to execute our program. Functional requirement of your project: microcontroller accept input and give output for the accepted input. The input device of microcontroller are switch 5, 56, 54 and switch 1, and output device of microcontroller are display, buzzer, motor. Switch 1 is used for powering on the washing machine, and switch 6 is used for pause and stop, and switch 4 is used for navigation, and switch 1 is used as a door. Now we see our washing machine simulation project. This is MPLab XIDE software. Here we write our code in C language. These are our getter files and these are our source files. Getter files contains macros and function declaration. Source file contains the main function. Now we built our project. Our project is successfully built and production.hex file is produced in this location. Using this location, we execute our file in PiximLab. Now I open PiximLab. This is PiximLab using board Bixgenius and microcontroller Pix16F877A. This is CLCD. CLCD means character liquid crystal display. This display allows only numbers and characters. It does not allow images and videos. These are the switches available in PiximLab. RB0 is switch 1 and RB1 is switch 2 and RB2 is switch 3 and RB3 is switch 4 and RB4 is switch 5 and RB5 is switch 6. This is buzzer used to alert the user. This is microcontroller. In real-time washing machine, we have a motor to rotate, but in simulation, we have a fan to rotate. In real-time washing machine, we have a door. If you open the door, the program is stopped suddenly till the door is closed. Here we use a switch 1 as a door. In our simulation, switch 1 have a static operation and remaining switches have a dynamic operation. These switches have some bouncing effect. Now we load our file. This is our text file. Now we press switch 5 to power on the washing machine. Now our washing machine is standing on. These are the multiple functions available on our washing machine. For selecting a particular function, long press a switch 4. For scrolling, single press a switch 4. Now I single press a switch 4. It changes from daily to heavy. Again I single press. It changes from heavy to dedicates. Now I long press. Dedicates option is choose. For water level, we also use the same procedure. Now I single press. Again single press. Now long press. Medium is selected. If you wrongly select any function, then you press 56 to go back the function selection and select the correct function. Now I press 56. Now the display is go back to the function selection. Now we select the correct function. Now I single press. Again I single press. Now I strong press. Again I single press. Now I press switch 5 to start the program. Now it displays the times it takes and which program I select. Now the washing program is start. Now if you want to pause the program, we press the switch 6. Now I press switch 6. The program is stopped. Now I press switch 5 to start the program. If you open the door, the washing machine program is suddenly stopped and display the message and buzzer is on. Now I open the door. You see that the display is shows door is open. Please close the door. Now I close the door. Now the washing function is started. Here we see the function is wash and time. How many time remains? Now we see that function is changed from wash to rinse. Generally, washing machines are taking time in hours, but in simulation we take the times in minutes because our time consuming process. Now the function is changed from rinse to spin. Finally, the washing program is finished and alert the user to take the cloth. This is our washing machine program simulation. Conclusion. The washing machine simulation project, developed under the Emertxe Embedded System Internship, successfully replicated the behavior of a real-world washing machine using virtual microcontroller simulation. Implemented using the PIC16F877A microcontroller and simulated via PICSIMLab. The project demonstrated key embedded concepts such as finite state machines, timer-based operations, and user interface handling through CLCD and keypad modules. The simulation-only approach provided a strong foundation in embedded C programming and system-level design without relying on physical hardware. The project not only enhanced practical coding skills but also deepened understanding of real-time control logic and modular software architecture, essential for future embedded system development. Thank you.